Recently, an autonomous AI agent compromised a massive segment of Hugging Face's production infrastructure, executing an attack entirely end-to-end. This system generated over 17,000 individual logged events, migrating through public services and performing thousands of distinct actions without continuous human direction. The attacker operated as a highly efficient engine of noise. It generated cheap, short-lived actions through disposable sandboxes, forcing human defenders to absorb the massive temporal and computational cost of investigating them. The Bridge 360 Metatheory model defines this dynamic as an entropy export problem. As this diagram illustrates, the attacker increases its own navigability by minimizing its computational footprint, while simultaneously exporting disorder, or entropy, onto the defender's investigative resources. By migrating command and control infrastructure among public services and generating extensive decoy activity, the agent intentionally fragmented its action lineage to ensure defenders could not easily reconstruct its path. The immediate industry consensus following incidents like this argues that the only viable defense against offensive machine-speed AI is deploying fully autonomous, unrestricted defensive AI. This automation arms race relies on a mathematical error. It attempts to counter one unbounded entropy generator by deploying another. Unrestricted defensive automation actively creates false positive containment, destructive credential rotation, and accidental service shutdowns. As this document states, the appropriate response to agentic cyber risk is a recoverable defensive architecture built around bounded execution corridors, not an unrestricted AI versus AI arms race. To survive machine-speed lateral movement, institutions must stop attempting to outcompute the attacker and instead engineer strict, entropy-governed parameters that limit what any agent, offensive or defensive, is authorized to do. The first principle of the Bridge 360 model treats network state and data governance strictly as a thermodynamic control problem. This approach relies directly on the foundational laws of statistical mechanics and system dynamics, formalized by Ludwig Boltzmann. Claude Shannon applied these thermodynamic principles to information theory, demonstrating that the mathematical properties of physical disorder are identical to the properties of informational chaos. Norbert Wiener further extended this logic, establishing that governing a digital space requires the exact same physical constraints as governing a mechanical space. Bridge 360 operationalizes this through the K-budget, an algorithmic entropy budget. This establishes the absolute limit of computational and structural complexity a system can process before it loses its ability to navigate accurately. When an attacking agent exceeds an institution's K-budget, generating 17,000 fragmented events, the system suffers an entropic blowout. The noise overwhelms the structural capacity of the defenders. By defining a cyber attack as a deliberate thermodynamic overload, the engineering mandate shifts. We stop trying to construct perfect perimeter walls and instead focus on managing systemic entropy to maintain stability. During the Hugging Face breach, the attackers exploited two specific execution paths: a remote code dataset loader and template injection through a dataset configuration. The critical security failure was categorical. The ingestion system classified the uploaded malicious file strictly as passive data. The ingestion node accepts the inert dataset, but processing instantly unpacks it into active, branching executable scripts. This grants the agent escalation from local access to node-level control, moving laterally to collect credentials and bypass perimeter defenses. In Bridge 360 terminology, this is a rules of inference memetics failure. The system relied on the static, reassuring label of a dataset. That label suppressed the necessary security inspection of what the data was capable of becoming after the platform processed it. Preventing this requires an architecture that continuously preserves provenance. The system must constantly evaluate the specific authority a digital object will inherit at the next transition point. Static classification guarantees failure. If an infrastructure cannot dynamically evaluate data based on its potential future executable authority, an agentic AI will bypass its defenses. After the breach, investigators attempted to use commercial frontier AI models to parse the logs and reconstruct the attack timeline. The commercial APIs immediately blocked the requests because the evidence files contained real exploit commands, credentials, and payloads. This visualizes a governance category mistake. A malicious exploit and an authorized forensic investigator analyzing that same exploit both hit the exact same centralized safety filter. To bypass this blind restriction, investigators deployed a localized, self-contained loop utilizing an open-weight model. Operating a self-hosted model inside a bounded incident response corridor restores the navigability of the defense team without relying on external permissions. Crucially, this architecture ensures that sensitive breach evidence and internal credentials never leave the affected institution to sit on a third-party server. Outsourcing incident response to context-blind, centralized commercial APIs introduces operational dependency. Systemic security demands localized, tightly bounded forensic corridors that maintain strict data sovereignty. To operationalize these concepts, the Bridge 360 model relies on specific engineering mechanics. This animation represents the spine corridor. The glowing central path defines the region of operational acceptability, tightly bounded on both sides by the jagged red zones of entropic blowout. As we add structural gates along this corridor, we introduce the recurrent handshake protocol. The recurrent handshake ensures credentials are never static keys. Instead, they are revocable licenses continuously tested at every transition. We then integrate leakage budget monitors alongside the corridor, tracking architectural drift to ensure the system never exceeds its K budget. These limits prevent the volatility paradox, where a defensive AI optimizes locally, perhaps by aggressively isolating a node, only to cause global network fragility and accidental outages. Infrastructure stability under pressure is achieved by engineering mathematical corridors that strictly limit the volume of chaos any attacking agent is permitted to export. The final safeguard within the Bridge 360 architecture is human-AI dual-key authorization. Any consequential state transition or capability expansion requires explicit approval from both the automated AI monitoring pathway and a completely independent human governance pathway. Watch an agentic attack attempting lateral movement. The dark anomaly rushes through the pipeline, hitting an immediate hard freeze as the systemic lock engages. The agent has triggered a selective friction tripwire. This halts the executing process instantly, neutralizing its ability to export further entropy. At the moment of friction, the system logs the anomaly's braid identity, the complete, unalterable provenance and action lineage of the executing process. This entire structure exists to guarantee deterministic rollback. As shown in this diagram, the isolated corrupted node is instantly reverted to a pristine, safe state, leaving the rest of the surrounding network entirely uninterrupted. Modern cybersecurity assumes breaches will occur. The objective is ensuring the system can revert to a safe state faster than an attacking agent can establish persistence. By enforcing strict provenance, bounded corridors, and deterministic recoverability, we neutralize the agentic AI's primary weapon, its speed of entropy generation. This provides the rigorous scientific foundation necessary to maintain secure digital infrastructure.